Okay, are we doing it? Are we writing, please? It's going to be away until Wednesday. All right, guys. We get different types of points of inflection. We remember that point of inflection is where the second derivative is 0. All right, so if they ask us to find the point of inflection, that's what we do. We make the second derivative equal to 0. But then we get points of inflection that are also stationary points. All right, now a stationary point is kind of a turning point, but also not necessarily. It's a bit of an iffy topic. All right, just try and draw those diagrams. So you see that it's almost like a flat point there. All right. Maybe I must just show you the other type so that we can compare. It will make a bit more sense that way. The second type, those are actually the points of inflection that we are more familiar with. All right. So it's not a stationary point. But we can see that the curvature changes, the concavity changes. Can we just quickly look at the second one? Just stop writing quickly, guys. If we're looking at this first picture, do we see that for this part it's concave down? Then we have our point, then it's concave up. All right, so that is a point of inflection. So here, the second derivative would be equal to 0, but the first derivative is actually not equal to 0 because is it a turning point? Hey, is this a turning point? Is it changing from increasing to decreasing? Not. Same here, all right? Here we have a concave up part. Remember, concave up is like a cup. Do you guys remember that from last term? And then the concave down part. And this at that point is where the curvature changes. All right, so these are the points of inflection that we've dealt with in core mostly. So where you have your second derivative equal to 0, but your first derivative is not equal to 0. Okay, so it's a point of inflection, but it's not a stationary point. Now, what is happening here? If you have that your second derivative is equal to 0 and your first derivative is equal to 0, all right? We are going to look at some examples, but this would be where you have a double turning point. All right, do you guys remember, if we just think back to last term, if you have a double x-intercept, it's an x-intercept and it's a turning point. Do you guys remember that? In the same way, if you have a double turning point, it's a turning point, but it's also a point of inflection. All right, so that is what's happening here. It doesn't look like a turning point though, because what happens at a turning point usually? It goes from being increasing to decreasing. All right, so it's increasing on the one side and decreasing on the other side. Is that what's happening here? No, we can see that it's actually increasing on this side and then on the other side. But if we technically have two turning points at the same point, it's almost like it's turning twice, which is a bit of a weird way of saying it. But it's like a turning point and then another turning point, and it's at the same point. I don't know if that makes sense. That's why we have to draw it with like a flat bit there at the point of inflection. All right. So this is where we are going to do examples. So don't worry if it doesn't make sense now. All right, we will do examples. But this is actually a double turning point, which makes it a turning point and a point of inflection. All right. Maybe I must just add that here. Okay. But guys, this is not really something that will ever come up in core, all right? They're not finicky about what type of point of inflection you have. It only really comes up in AP and also not often, right? But the types of questions that we're going to do now is where they could maybe ask you to classify the stationary points that you have. All right, then you need to say it's a non-stationary point of inflection. You'll see now when we do the examples. Okay, technically they could ask you this in core, but they don't. Right, they don't ever go that far. So we're going to do some examples now. That is the first one. So you can just write examples and then number 1. Oh, this thing keeps sliding. I don't remember how to know if it's like how to know if the shape is going to be like that or like that. Is it like an A value? Yes, so the A value will tell you that. Yes, we're going to talk a lot about shapes still going forward. Okay. Yeah, so that for now we're just talking about that point. Now guys, if this was just, if the word non-stationary wasn't there, I think you all would have been perfectly fine, okay? Given f of x is that, determine the point of inflection of the function. Right? What would you do? Point of inflection, okay? Second derivative equal to 0. Do that, please. You have f of x, you're going to have to find the first derivative and then the second derivative. Make that equal to 0 and get that point. So do that on your own, please. Then we're just going to double check whether it is in fact a non-stationary point of inflection because they are being specific here. I'm actually not sure. I did want to Google that because I know that NSC exam timetable has been released. So I think. Do you want to check if you can find ID because it will be on there. Yeah, it's usually like a week before your NSC exam starts, but I don't know. I don't know with this year being so like weird. It should be like that. Okay, do we have an answer for that point? 0, -1, hey? Okay, so you obviously don't have to lay it out exactly like I did there. You find your first derivative, your second derivative, you make that equal to 0, solve for x. To get the y value, you would sub that x value into the equation. All right, obviously it's very easy to see here because you have 3 terms. So that would be 0, 0, and then -1. All right, so in this case, the point of inflection is actually also the y-intercept. Now guys, they did say non-stationary point of inflection. We can see that we're only getting 1 point of inflection here, all right? We are going to be working with higher degree polynomials going forward. So x cubed in core, that is as high as you will go, all right? In AP, we're going to go higher. So sometimes you will get multiple points of inflection, all right? You might not only get 1. In this case, because we've only got 1 answer here, we can assume that that is the non-stationary point of inflection, okay, because we only got 1. But let's just go over how we would check if we got more than 1. Now, this is important, guys. a point of inflection that is also a stationary point. So a stationary, a stationary point of inflection is one where your second derivative is equal to 0 and your first derivative is equal to 0. A non-stationary point of inflection is where your second derivative is equal to 0, but your first derivative not. So for non-stationary, the second derivative must be equal to 0. Okay, we have that there, but the first derivative not. So let's just add that there in the actual question. If we're saying non-stationary, the first derivative must not be equal to 0. And that's easy to prove, hey, because we have the first derivative. We know that the first derivative is 3x squared minus 3. What is the x value of the point of inflection? 0. If I sub x equals 0 in here, what is the value? -3, which is not 0, right? Which makes it a non-stationary point of inflection. There we go. So it's just almost like a little check that you're doing, but just add that in there. So to check whether it is in fact a non-stationary point of inflection, all right, stationary, your first derivative must also be 0 at that point. Non-stationary, your first derivative is not 0 at that point. Okay, either way, you must sub the x value into the first derivative. So we're doing that and we're getting -3, which is not 0, which makes it a non-stationary point of inflection. Okay, thank you.
But when you say under x equals 0, therefore in sub 0 to the actual function, is that meant like what?
No, you don't have to do that. I just did it for the sake of completeness. Yeah, you can just say 0 and -1 straight. Okay, so guys, it's basically just one extra step. And in fact, I don't really even think you would have had to show that extra step there because we're only getting one point of inflection anyway. All right. I don't think that's too bad. All right, let's look at the next one. You can just ignore this thing on the side. I'll show you now. So investigate the nature of the stationary points of. Now we're going to do more than one here. So the first one is x cubed minus 6x squared plus 12x. Now guys, if they're asking you to investigate the nature of the stationary points of a function, they obviously haven't given us the stationary points. All right, so we need to find them. Now, if they're just saying stationary points like that, you're actually going to have to find the first derivative and the second derivative. All right, so you're going to have to find the turning points and the points of inflection. Okay, so do that quickly, please. See what happens. I will uncover that pink bit just now, and then you can just add that there. So you're going to find your first derivative. You're going to find your second derivative. Make those equal to 0. See what happens. Guys, also remember that when you're in AP, you can use your calculator to solve all of the different equations. Hey, you never actually have to factorize or use the quadratic formula unless they are specifically asking for that. What do you mean higher order?
Like x to the factor of like 5.
Why do I feel like I don't know?
Yeah.
So it goes to 3. Yeah.
I think maybe that you factor like 1 squared.
Yeah, usually with an x to the 4 thing, it does. They'll usually give you ones that are like difference of 2 squares or ones that you can factorize into 2.
But can't use like the solve function?
Yes, you can. Yeah, I will still show you how to do that as well. Oh, and guys, while we're on that, before I forget, in your answer series book, they actually have like an addendum at the end where they show you how to do all of the fancy stuff on the solver calculator. So if there's stuff there that I haven't shown you yet, which there definitely is. Let me check quickly. Because I was thinking that I would tell you about that. It's appendix 1, which is right at the back. Yeah, it's like simultaneous equations, quadratic and cubic equations, equations using shift solve, which is what we're talking about, integrals, derivative. And then now the formula. Okay, let's take a look, guys. So my layout is possibly a bit different from yours, and you would also probably be missing some of this. All right, so let's just talk about that. Yeah, don't stress. Are we fine with this and this?
Yeah.
Derivative, second derivative. Now, guys, if you found the first derivative and you made it equal to 0 and you solved for x, you would have seen that you're getting x equals 2 twice, right? If you make this equal to 0 here, and you solve for x, oh, man, why does this thing keep freezing today? Okay. Yeah, you wouldn't have done the number line and stuff. Don't worry, don't worry. Today.
No, you said for long.
Okay, there we go. Okay, sorry guys, the thing was frozen. Okay, did you see what I added in pink there? If you make your first derivative equal to 0, you'll get, and you divide through by 3. Again, you don't even have to do that, okay? So remember, we're in AP now. We don't have to show factorizing. We don't have to show quadratic formula. So if you have this, you can put it in the calculator straight away and get your answer of x equals 2. All right? No working needs to be shown from there. So you would get x equals 2 as your turning point. All right, and then obviously 2 you can sub in there and you will get 8. All right, so your turning point will be 2, 8. Okay, is that fine? Then you would do your second derivative, make it equal to 0. You would also get x equals 2. All right? Yes?
If you knew that there was only one turning point in a cubic function, 0.
Yes, exactly. So this, if you did the factorizing, you would get x minus 2 squared. Right? If you factorize this, it would be bracket x minus 2 squared, which would mean that this is a double turning point, which would also make it a point of inflection. Okay? If you didn't know that, you could have just done it the old-fashioned way by finding your second derivative, making it equal to 0, and solving. All right? Now, guys, this is just what they did in the textbook, which is why I'm saying don't worry if your layout is different. Okay? It would have been because of the instruction that I gave you. So now, do we notice, and then there you would sub in, you don't even have to sub in because you can see that it's the same point, all right? So now, guys, we are finding a stationary point of inflection. Does that make sense? Okay, if you're getting a point where it's your turning point and it is your point of inflection, then obviously it is a stationary point of inflection. All right, yes?
I just have a question about the notation.
Yeah.
In a text or something, would it be better to just work it out instead of take your
question, because if they're just asking you about a point of inflection, then they're not going to think you now all of a sudden talking about point of intersection. But if they're asking about both, then you would, yeah, have to identify them. Now, guys, if you did it like that, right? If you found your turning point and then you found your point of inflection, therefore it is a stationary point of inflection, then you wouldn't have needed to do all of this stuff. Are we listening? I just want to go through what they're doing here, all right, in terms of checking concavity. But I'm going to say again, if you found your turning point, then you found your point of inflection, or even if you just recognize that this was a double turning point, therefore it is also a point of inflection, therefore it is a stationary point of inflection, right? Because it's the same point. Does that make sense? 2, 8 and 2, 8. It's not two different points. So you do have to, that's what they say when they say investigate the nature. You have to actually classify that. Okay, you can't just leave it as my turning point is 2, 8 and my point of inflection is 2, 8. You have to pull it together and you actually have to say it's a stationary point of inflection. Okay, that's what they're looking for. Now, what they do in the textbook is they don't actually even calculate the turning point, or this point, all right? They just do that. Then they find the second derivative, then they find the point of inflection. Then they try and classify the point of inflection and they're ending up with it being a stationary point as well, all right? Which is a bit awkward, but I did just want you guys to see that in case you see it in the textbook as well. So they're getting this x equals 2, and then they're doing this check that we did in the previous question. All right, they're subbing 2 into the first derivative and getting that it's equal to 0. Right? Meaning basically that it is a stationary point there. So now they're saying if the first derivative is 0 and the second derivative is 0, then it could be a local maximum stationary point or a point of inflection. So then they're checking concavity. What happens at a point of inflection, guys, in terms of concavity? It changes, all right? So that's why they're doing a little number line here. And on the number line, we're checking what's happening to our second derivative. This is the x value of that point. On the left, the second derivative is negative. On the right of that point, the second derivative is positive. And does that mean that concavity is changing? If it's going from negative, negative is concave down. So it's going like this kind of shape to concave up, right? So that is what it looks like. But guys, mine isn't really flat enough here. Okay, it's supposed to be a bit flatter. That is what the shape would look like at that point. Because it's not just a point of inflection, it's also a stationary point. Okay, so it should actually look a bit flatter than mine. Just draw that in. I don't even think you need to write this stuff down, guys. If you just did it like I explained now, you found that it's your turning point, then you're finding that it is your point of inflection, then you just need to understand how to draw it though. Okay, if it's a turning point and a point of inflection, it needs to be a flat one. Yes, Iman?
When you said
Yeah, that's what I thought as well, because there also isn't a different example in the book, one where it is one or the other. So I think just ignore that for now. If it comes up, then we can talk about it. Okay. All right, does it make sense, the shape, guys? Usually we don't actually even get asked questions like this. We're actually gonna have to apply this to drawing the graphs, which is what we're working towards. Okay, so just draw that little shape in there, please. Just make it slightly flatter than mine. Okay, it should go like flat and then up again, just to show that it is actually a double turn point. So it's like it's turning twice on one little line. Okay, let's look at B. Oh, it's happening in the next one, Iman. Yeah. So we can chat about it there. Okay, the next one, there is B. So giving us that equation. Now we have an x to the 4. All right, let's just think about this quickly in terms of derivatives. If we have an x to the 4 as our original function, the derivative is going to be a cubic function. And if we then make that derivative equal to 0, how many turning points do we expect to get? 3. Our second derivative will then be a quadratic function. If we make that equal to 0, how many points of inflection are we expecting to get? 2. All right, so now this is where the whole investigating the nature of it comes in. Okay, I'm just also going to try and rewrite it. You can do it on your own, all right? Stationary points and then classify them. Just going to do it here in a different way as well from what I wrote. Yes, it is a triple turning point. Yes, we'll see now what happens when we get that. There isn't another name for that. It's not like a third derivative thing, but yeah, double point of inflection, yes.
It's nice when I'm saying it's great. There's so many funny names off the process of what we're doing.
Yeah.
I can do them.
Yes, sure. Yeah, so now imagine we have to draw that graph, guys. What would we even do? Hey, that's a bit. Get off the crying. Okay, guys, let's just quickly stop there before we actually classify it. Let's just discuss what's happening here. All right, did we get that? So we're making our first derivative. When we make that equal to 0, then we get x equals 2. Sorry, I forgot to actually write equals 0. That is important. And that also, please. My bad as well. All right, so we make those derivatives equal to 0. We see that we're getting only one x value, and it's also, again, the same x value in both of them. Now, guys, because of the type of function that we have here, we do actually need to check what is actually happening here with the shape. All right. Now, I know that the first derivative is equal to 0 at x equals 2, and the second derivative is also equal to 0 at x equals 2. Now, this is where this situation comes in. Sorry, this on the previous page, where they were saying, if you have that happening, all right, the first derivative equal to 0 and the second derivative equal to 0, all right, it could be a local maximum or minimum stationary point or a point of inflection, All right, so that's what Iman was asking for. Mustn't it be and? And it will be and if it's a cubic graph. Okay, but as we're moving up to the higher graphs, something else might happen. Okay, so let's just quickly see there. Sorry, I'm having to page back and forth here the whole time. So now the easiest way actually to check what is happening here, what type of stationary point this is, would be to check the concavity. All right, you'll see now what happens when we actually do that. So the x value that is of value here is 2. We're going to sub a value into the left or on the left of 2 and on the right of 2 into the second derivative. That's going to tell us what the concavity is like. Okay. So let's do 1. If we're subbing 1 into this, all right, what are we going to get? 12, so a positive value, thank you. And then if we're subbing in 3, also 12, interesting. So we can even write that down, the fact that they have the same y value. So we have 1, 12 and 3, 12. So what do you think, guys? Remember at 2, the second derivative is 0, right? We know that. So it's concave up, 0, concave up.
It has 2 points of inflection happening.
It's a double point of inflection, right? Because it's an x squared, so we're supposed to get 2 x values here. So this is a double point of inflection. And it is a triple turning point.
And it would just look like a quadratic.
Yes, but with a flat width. Well, they would see. I'm not actually going to write as my answer triple turning point. We're going to have to state. You'll see now when we do the shape. But possibly, yeah, you could kind of what's the word? Reason from there. Now, guys, if we think of this, doesn't this remind us of a parabola? Right? We have our turning point, all right, and then we have concave up, concave up. But now we can't do that because in the case of a parabola, is that turning point also a point of inflection? Look at how this is going to look. Sure, I actually don't want to draw it. I have it there. It's going to look like that. All right, we have here that the concavity does not change, which I added on my original working. Basically, what we have is a flat point of inflection because it is a double point of inflection, right? Every time it's a double, there must be a flat bit, essentially. Okay, so it's almost like your concavity is changing twice. So it's concave up and then it's changing to concave down, but you can't really see it, and then it's changing to concave up again. Does that make sense? All right.
If you like did it on like graph software, you zoom in very close. Did you see it changing?
Yeah. Oh,
Like what is it? What actually happens? Like to the graph. Like obviously you just draw it flat, but is it actually flat? Like no matter how close you zoom in.
sure. I mean, I haven't zoomed in. Actually not. Yeah. I'm not sure. I think because Alex has a graphing calculator as well. Maybe we can check. I'm not sure actually about that. All right, but guys, does that kind of make sense? So in this case, we're going to have to call it a local minimum turning point. Weird, hey? Local minimum turning point. Because isn't that what's happening? Right? It's going from being decreasing, then you have your point, and then it's going to increasing. All right, so this is a very funny one. Very strange one. It is in actual fact a local minimum turning point. So unfortunately, you can't write triple turning point or double point of inflection. All right, you will have to say local minimum turning point. They didn't ask for the shape, but it's useful to actually just draw it in there for future reference when we're actually going to draw these graphs. Yes.
Can I please see what you wrote in the paper on the last? Because at the time I was
In the last one, in number 2.
yes.
Yes, okay, let me quickly show you. Yeah, so guys, maybe you should just write that in there, because that is now actually something that occurred in this example. It probably would have been better to write it for the second example, but I'll go back to the next page just now. Just write that in some way. So guys, if you're not actually sure of what's happening, check the concavity on either side of that point. All right, and figure out what the shape would be. Especially when we're actually going to draw these graphs, the shape is going to become quite important. Figuring out what is the sign of the function, the sign of the derivative, and the sign of the second derivative. All right, so yeah, we're going to practice a lot of these. Yes. Okay, say again. Yes, so we kind of ignore the one that is unseen, if that makes sense. Yeah, but I hear what you're saying. Okay, do we write that down? Just this part here? Okay, let's just go back, and then I don't really know if we should do number 3. Oh, sorry. Alex there? Yes, therefore, and then, sorry, then that is the final. So yeah, so it's basically the pink, and then that's the final answer. So it's just because it's going, yeah, it has a little wire. Yes. No, because in the check we kind of did it already when we solved for x. Yeah. Because again, other stuff could be happening further on. Well, it is going to go and on the end. Yeah, it will. Okay. All right, guys, I want us to look at that worked example 17. Are we listening? Thank you. I'm not going to do the last example now. It's just more of the same stuff, basically. On the pages that I handed out last term, that x-intercept thing, that worked example 17. Let's look at that quickly. And guys, this kind of seems a bit disjointed, but they kind of, are we listening? They kind of covering separate aspects of the graphs before putting them all together and having us draw them. Okay, so that's why we looked at the local maximum minimum point of inflection. Now we're going to look at the x-intercepts. So guys, you need to be able to draw those graphs, eh, by the way. Not as bad as it looks. Not as bad as it looks. For now, yeah, it's actually, yeah, it's quite fun. I enjoy it. All right, guys, they are just saying here, compare each of the following functions with the graph. Comment on the type of x-intercepts. Are we listening? Thank you. Now they've given these equations in factorized form. All right, which is obviously quite useful if we need to comment on the x-intercepts. So if we were to make this equal to 0, we would get -3 as a normal x-intercept and 1 as a double x-intercept. So 1 would have to be a turning point as well. Is that happening? Yes. Okay, so we could draw this one quite easily. All right. We have an x-intercept of -3, which we're getting from that bracket, and an x-intercept and a turning point from this bracket of x equals 1. Because it's a double x-intercept, it will also be a double, but not double, sorry, it will be a turning point as well. All right. And the point of inflection will be here somewhere if they were asking for it in this case, they're just asking us to comment on the x-intercept. Next one, we have x squared, x plus 1, x minus 4. If we were to multiply this out, what would the degree of this function be? X squared times x would be x to the 4. Right, so this is an x to the 4th degree polynomial if we were to multiply it out. If we are making this equal to 0, we're going to get 3 separate x-intercepts. Do we see that? We're going to get x equals 0, but because it's an x squared, this one would be a double x-intercept. All right, so also a turning point. Do we see that? Where am I now? At 0 there. Right, do we see that that's also a turning point? It's just quite small there, but maybe look on your own pages. All right, that is a turning point. That would give us the x-intercept at -1, which we have there, and an x-intercept at 4. Right? We're not going to worry about the shape now. We'll discuss that later. We're just talking about x-intercepts. Next one, we have x squared, we have x plus 1, then we have x minus 2 cubed. All right? So what would the degree of this function be if I were to multiply it all out? X squared times x cubed. X to the 6, eh? All right, interesting. There we have an x squared. So this would give us an x-intercept of 0, but because it's a double x-intercept, it would also be a turning point, and we see that on the graph, right? This would give us an x-intercept of -1. It's just a linear one, so that's just a normal x-intercept. And x minus 2 cubed. What is this? A triple x-intercept will give us a double turning point, which would give us a point of inflection. Do we see that that is a stationary point of inflection because it's going flat there? Okay? Okay. Maybe, and I'm sure this is the case when we actually are drawing these graphs, some things will start falling into place. Okay, so please don't panic now. We're just discussing. We are building up towards actually drawing them. Here we have x plus 1, x minus 2 to the power 4. So this is going to be an x to the 5, okay? So that is a normal x-intercept at -1. And this is now like what we had in the previous example, where we have an x-intercept. What is that? A quadruple x-intercept. All right, which will give us a triple turning point, which will give us a double point of inflection. And isn't that like what we saw in the previous example, where it looks like a local minimum turning point, hey, but it's actually also technically a point of inflection, right? This looks like this is what I'm saying. This is my book. If we're looking at that, x equals 2, and coincidentally, it's also at x equals 2, all right? That wasn't planned. It's that kind of shape that we have over there. Okay, because it's a double point of inflection. Right, does that make sense, guys? I'm not making this stuff up, eh? We can see it's actually in the textbook as well. Yes? Triple x. Okay, now guys, let's highlight this, please. Let's highlight this, please. I know we leave it soon. Let's just finish up nicely. Okay, just read through that in the block and just see if it makes sense. I'm going to explain it now. Just basically conclusion from all of those examples. So they're saying that if you have a bracket as a factor of a polynomial function, and that bracket is to some power, all right, and the power will be a whole number. If that power is odd, so remember 1 is also an odd number. Hey, so if you have like an x plus 1 to the power of 1, that will just be a normal x-intercept. If we're looking at the first one, for example, that is what they're talking about when they're saying that the exponent of that bracket is odd. All right, do we see that the graph is just cutting or crossing, rather is the word that they're using. It's crossing through the x-axis. All right, Do we have something here? Both of those are also odd, all right? The exponents of the brackets are odd for both of these. Again, the graph is just crossing through the x-axis, all right? Over here, the x minus 2 cubed, 3 is also an odd number. So at 2, again, it's crossing through the x-axis. All right, so that's that first sentence where they say, if a bracket is a factor of a polynomial function, if the exponent of that bracket is odd, then it will cross through the x-axis at that value, all right? But if that exponent of that bracket is even, then the graph will have some kind of turning point, all right, on the x-axis, whether it's a double or whatever. Okay, so here we see that. Here we have an even exponent of that bracket. So we have a turning point at that value. That's not a bracket, but I mean, technically you could say it's x minus 0 squared, all right? Just if it's x squared. So there at 0, we again have a turning point. There, even exponent, turning point. Even exponent, turning point. All right, so that's quite useful. Yes. Yeah, so it's like going through the x-axis. Yes, so going from negative to positive or positive. Yeah. Okay, so guys, you're not going to have any homework for today, how nice. Just to give you an idea of what we're doing tomorrow. All right, we are doing AP again tomorrow. We are going to discuss, hello, I'm so busy, thank you. We are going to discuss this table and we're going to draw some graphs. All right. Let's take at night. I just want to, sorry.